tangerine trees and marmalade
Is LSD hydroxylated in vivo? This is an important question from many, many years ago, which could help us understand why some people may have bad trips when they take this compound. The story starts with Lurgo trial. Lurgo trial was looked at for treatment in Parkinson's disease because it is a dopamine agonist, but it was quickly discontinued because it had some liver toxicity. The Lurgo trial is hydroxylated in the 13th position, and this compound is about 100 times more potent in suppressing prolactin production, which is directly correlated to the activity at dopamine D2 receptor. Okay. We had also made this 6-hydroxy tetraline, which also displayed higher potency D2 receptor in general. Whenever you have an ergoline compound or an indole alkylamine, this substitution will produce dopaminergic compounds, most notably potent compounds at D2 subtype. Today we know that LSD has a biphasic pharmacology. After ingestion, we'll have activation of 5-HT2A receptors, and then we will have maybe like 1 hour gap, and then at 90 minutes, this metabolite will start hitting D2 receptors. And why is this important? Because D2 receptor is involved in schizophrenia. We use haloperidol, risperidone, drugs that block this receptor to suppress these symptoms of schizophrenia. And if indeed that happens with LSD, this can very well explain why some people have not such a pleasant experience or a bad trip after 1 or 2 hours, most notably after 90 minutes. And we can basically teach the rats to distinguish various drugs. We can teach them to distinguish mescaline, 2CB, LSD, MDMA, whatever we train them to do so. And we had a mice trained to distinguish the stimulus many, many years ago. And today we know that LSD is indeed hydroxylated in the 13 and 14 position. You can buy the glucuronide. Most likely it is produced by just exposing LSD to liver microsomes, and then you can collect the ester. The free hydroxys are extremely unstable. Those things cannot be made. I had a friend during my doctoral years who spent 4 years trying to make not just LSD, any kind of ergoline nucleus with the 6-hydroxy. It was all fruitless. The major metabolite is this 2-oxo 3-hydroxy. Basically, that is the first site that gets attacked, and that is why all indole alkaloids and tryptamines are antioxidant, because they accept oxygen. Okay, this is all done by the liver. This CYP enzyme 3A4 oxidizes the 2 position and also dealkylates the N6.
Aww.
A human death from an LSD overdose has never been recorded. Rabbits seem to be the most sensitive species to this drug. Then rats and mice tolerate even higher doses. Monkeys have been injected with doses as high as 1 mg per kg without any serious long-lasting effects. I have heard a story where they injected an elephant with about 300 milligrams of this drug, and the poor thing died shortly thereafter. It's a really, really high dose if you extrapolate. The fellow who did this used to work for the CIA and was involved in the MKUltra project. A very sad and a cruel thing to do. In rhesus monkeys, we can see these 4 metabolites. They have been isolated and characterized fully. In humans, we still don't know what we make, because we can see only one peak corresponding to 13 or 14 hydroxy LSD in the mass spec, so we don't know, do we make both of them or only one, or in what proportion. It is also worthwhile mentioning that there is genetic polymorphism of these liver enzymes, and that determines how fast or slow we metabolize not just LSD, all psychedelics, and it will determine our sensitivity to these compounds. What I think that is really going on is that these species are formed directly on the brain and where they can act upon dopamine receptors immediately. If this were to happen in the liver, uh, you would still need to somehow transport the compounds to the brain via blood or plasma. And I think that these compounds are very unstable. I don't think they will ever be made in the lab. And I think this is a more plausible mechanism. So there have been two publications where they did really oxidize LSD using either horseradish or meal peroxidase. These enzymes contain a heme and an iron center, and they produce superoxide and hydrogen peroxide, which are very high energy oxygen species. And NPOs also oxidize DMT, tryptophan, serotonin, and melatonin. Right? Products from from this metabolism can be compounds that are neuroprotective or neurotoxic. The most interesting thing is that a certain cancer cell line of melanoma can indeed oxidize DMT. So I have no doubt that LSD, probably just a tiny little bit, is formed by this reaction in the brain. I should mention Iso-LSD, which is a synthetic contaminant. It is not a human metabolite. It is found in all street acid, depending on the skill of the chemist. The batches can vary from about 10 to 70% of this compound, and it is not psychoactive, and it has a higher half-life compared to LSD, about threefold. Now, if you want to make pure LSD, this is the way to do it. This reaction was developed by my buddy Stuart. Hoffman used phosphorus oxychloride for this amidation reaction, but the yields were only about 40%. If you use PIBOP, which is this fancy peptide coupling reagent, yields go up to 90%. Then you have to purify the free base LSD, which has this Iso-LSD contaminant, by doing a radial chromatography with a chromatotron. And it is a real art to do this because you have to literally make, bake, and cut the plate. And many times it cracks or breaks. You have to put it in the oven 8 hours, then scrape the surface. Once you get it right, you load it onto the chromatotron, start rotating it about 800 RPM. You load the sample near the center of the circle, and then just elute with hexane for about 4 or 5 hours. Then start adding dichloromethane in increasing amounts. This has to be done under ammonia atmosphere, otherwise the lysergium might just stick to the plate. And after a while, you will see two bands eluting, and the first pale blue fluorescent band is LSD. The second one is Iso-LSD. Once you elute it, the clock starts ticking. All the lights in the lab have to be switched off. You work only under a red or yellow light. You have to evacuate it, add an equivalent of L-tartaric acid, make the tartarate salt, precipitate it, crystallize it, filter it under nitrogen or argon, and put it in the vacuum pump overnight. And then you make pure LSD. Only a few people in the world know how to do this. Here we can see LSD docked into the dopamine D2 receptor active site. It has a binding energy of about 8.6 kcals per mole, and there is a hydrogen bond between the serine 193 and the indolic nitrogen. There should be a salt bridge formed with the N6 and the aspartate 114, but that is not shown. LSD is a partial dopamine D2 agonist. Let us look at the 14-hydroxy. LSD, and 14-hydroxy binds with a lower energy of 9.17 kcals per mole, and there is an additional hydrogen bond interaction with the threonine 119, while the 14-hydroxy binds with serine 197. Okay, and let's look at the 14-hydroxy now. The 13-hydroxy. 13-hydroxy is the most potent of the series. It has a binding value of minus 9.4 kcals per mole, and the indolic hydrogen bond to threonine 119 is maintained, and instead of 197, the 13-hydroxy binds to serine 193. So this may very well be the culprit behind some of the bad trips that users experience. This is produced after 90 minutes of ingestion of LSD and then starts hitting dopamine D2 receptors. And activation of dopamine D2 receptors is associated with schizophrenia. We treat this disease by dopamine D2 antagonists, blockers like risperidone and haloperidol. What is very interesting to mention is this serine triad right here, 193, 194, and 197, extending this complex hydrogen bond network up to threonine and aspartate, further up the receptor. And both D1 and D2 display this serine triad here, and it is very important for achieving selectivity, and I can show you that in a second. Okay. Let us look at the compound on the right. It is A77636. It's a compound made by Abbott Laboratories. It's a full and selective dopamine D1 agonist. It is nootropic, and it has profound anti-Parkinson's activity. It's been looked at as treatment for cocaine addiction. And it is an isochroman compound. We can see that both of these hydroxy from the catechol ring interact respectively with serine 198 and 202. Okay, that's shown with the yellow arrows. And if we just move this oxygen, instead of the isochroman, we make a chroman compound. And this compound I made for my PhD thesis. This series of molecules become very D2 selective. And instead of binding in this fashion, this orthohydroxy becomes unavailable for participation in hydrogen bonding with the receptors. So the meta-hydroxy binds both of these amino acid residues, while this orthohydroxy makes an intramolecular hydrogen bond. So there's only this orientation of this hydrogen that switches 180 degree makes a whole difference, making one compound D1 selective and the other one D2 selective. What a difference an H makes. Thank you. I hope you liked the video.